So the third talk is made by Kolshi Tojo.
Yes.
And a q-analogue of the family of Poincaré distributions on the upper half plane.
Can I use it?
I guess you can.
Yeah, you can. Here the laser pointer here.
There's a pointer here.
Laser pointer here and forward, backward. Forward and backward. Okay. Thank you for the introduction. This talk is based on the joint work with Taro Yoshino, who is an associate professor at the University of Tokyo. First, let me introduce myself shortly. I'm a postdoc researcher in mathematical science team at RIKEN AIP. RIKEN is the biggest research institution in Japan, and AIP is a kind of department studying artificial intelligence. And my research field is Lie group theory and representation theory, which is a study of symmetry of spaces. My hobbies are swimming and singing and shogi. Shogi is a traditional board game in Japan. It is like a chess. Yes. Then now let us show the let us share our aim of this research. One of our aim is to suggest good family of probability distributions on important spaces. To attain purpose, we propose a method using representation theory. This is a family of distribution obtained by our method. We call this family the family of Poincaré distributions with three-dimensional parameters. Now this is our content of this talk. First, we take much time to share our big picture of our research, and next we give a main theorem. Now let's enter the motivation part. First, learning by using family of probability measures is one of important methods in the field of machine learning. Here, learning is to optimize the parameters in the family of probability measures. We often use exponential families as a probability model. Exponential family are important subject in the field of information geometry. And exponential families are useful for Bayesian inference. And exponential families include many widely used families. Typical example of exponential family is a family of Gaussian distributions, like this. And these are examples of exponential families. Here, these are the sample space, Euclidean space. But for example, Wishart distribution is a kind of generalization of gamma distribution. The sample space is symmetric matrices with positive definite symmetric matrices. And for example, for me, this distribution is a family of distributions on the sphere, one-dimensional sphere. This family of distribution has been well studied in the field of directional statistics. And the Poincaré distribution is a family of distributions on the upper half plane. Here is our definition of exponential family. First, we take a manifold X and consider the set of all random measures on X. We denote by Rx, and a subset P of Rx consisting of probability measures is an exponential family on X if there exists a triple mu Vt satisfying the following four conditions. The first three conditions is a trivial condition. I mean, mu is a random measure on X, and V is a finite dimensional vector space of R, and T is a continuous map from X to V. And the fourth condition is the most important condition. That is, for any element P in P, there exists a dual space of, there is an element of dual space of V satisfying this equality. Here, phi theta is a log normalizer, and we call the triple mu Vt a realization of P. A family of Gaussian distribution is a typical exponential family on the real line in our sense. In fact, we can take a triple mu Vt like this. A second example is Poincaré distributions, which is shown in the at the beginning of this talk. That is, the family of Poincaré distribution is an exponential family on the upper half plane. This is a explicit form of Poincaré distribution. This is a parameter space. So parameter space is the set of positive definite symmetric matrices of size 2. In fact, this is exponential family in our sense because we can take a triple mu Vt like this. Okay. Now, in these days, we have there are a lot of phenomena that cannot be analyzed by the exponential families. So that kind of phenomena has been arising recently. So we often use Q exponential family as well. Q exponential family is a generalization of exponential family. In fact, if Q is equal to 1, then the family of Q exponential family is nothing but exponential family. And Q exponential family is important in the field of information geometry, and is useful for Charles statistics. This is inclusion relation. There is a example in the Q exponential family, Cauchy distributions and Q Gaussian distributions. This is a relation between the exponential family and Q exponential family. And exponential family is a Amaris alpha family with alpha 1. And exponential family arises as a solution of maximization problem of Shannon entropy with expectation constraint. On the other hand, Q exponential family is essentially Amaris alpha family with this equality. And Q exponential family arises a solution of extremization problem with of Charles entropy with Q expectation constraint. To introduce a definition of Q exponential family, first we introduce a definition of the function xq. Here Q is a real number, and we consider the subset of real line like this. This. And this is the domain of XQ. And we define the XQ by this formula. This XQ function is defined as the inverse map of the Q logarithm function, which is defined this formula. This is naturally defined by using integral. Now let us define the Q exponential family, which is an analogy of exponential family. Here, subset P of Rx consisting of probability measure is a Q exponential family on X if there exists a triple mu Vt satisfying the following four conditions. The first three conditions are the same as that of exponential family, and fourth condition is a little bit different. Here, for any element nu in P, there exists a element theta of dual of V and phi theta in R, satisfying these conditions. First condition means that this part is in the domain of the Q function for any x. And the nu can be described as this form. We call mu Vt a realization of P. Let us see an example of Q exponential family. Typical example is a family of Q Gaussian distributions. Let Q be a real number with in this interval, and then the following family of Q Gaussian distribution is a Q exponential family on the real line. This is a normalizing constant part. It can be described with explicit form. In fact, this is Q exponential family because we can take a realization mu Vt like this. This is the same as that. This is the same as that of normal distributions, Gaussian distributions. Now let us see the background of our research. By the definition of Q exponential family, there are too many Q exponential families, but only a small part of them are widely used, like this picture. It's too small to see, so let us enlarge here. Then we can find the famous family of distributions. So we can expect that there exist good Q exponential families. So we want a framework to understand good Q exponential families systematically. This is our motivation of our research. The following of the observation is a hint to attain our purpose. Namely, widely used Q exponential families have the same symmetry as the sample spaces. Mathematically speaking, sample space is a homogeneous space G mod H. Here G is a Lie group and H a closed subgroup of G. And the family is invariant under the induced D action by the push forward of G, D action. And here, good means having a symmetry namely mathematically G invariant as a family. Here, G mod H is a description focusing on symmetry of the space X. For example, the real line has a symmetry of scaling and translation, so we can describe the real line as a homogeneous space like this. And this two-dimensional sphere has a symmetry of rotation group, and so we can describe sphere like this. And the upper half plane has a symmetry of linear fractional transformation of SL2R, so we can describe the upper half plane like this. Here, let's see the meaning of the G invariance. Q-Gaussian distributions has a symmetry of scaling and translation. In fact, Q-Gaussian distribution is scaling and translation invariant. This means that the measure transformed by scaling and translation from Q-Gaussian distribution is also a Q-Gaussian distribution. So based on the observation, we propose a method to construct G-invariant exponential families on G mod H by using representation theory, which has two advantages like here. But today I do not explain detail of this method. Today's target is this area. That is the intersection of Q exponential families and family with symmetry. Q-Gaussian distribution is a typical example of this area. About this area, we remark that we do not have so many examples of Q exponential family on the homogeneous space G mod H, satisfying the following two properties. The first property is normalizing constant has an explicit form, and the second property is the family is G invariant. The Q-Gaussian distribution is only an example I know. And these properties has important because if the family has a first property, then it enables us to perform practical inference easily. And the second property is closely related to transformation models, which have been studied well and useful for Bayesian learning using Lie group. So we want to consider this problem today. That is, the problem is to give us example of Q exponential family on G mod H, satisfying the following good two properties. That is, normalized constant has an explicit form, and the family is G invariant. First, we observe the Q-Gaussian distributions. Q-Gaussian distribution can be considered as a q-analogue of Gaussian distributions, and this is a Q exponential family. And moreover, both Gaussian distributions and Q-Gaussian distributions are scaling and translation invariant. And on the other hand, we have important distributions called Poincaré distributions, which has a symmetry of SL2R. So our target is today is here. That is q-analogue of Poincaré distributions. This is our main theorem. We fix a real number q in the interval 1 to 2, and then the following family of distributions is SL2R invariant q-exponential family on the upper half plane. This is a explicit form of q-analogue of Poincaré distributions. This C theta is a normalizing constant with explicit form. And moreover, this family of distribution is SL2R invariant, and the action of the SL2R on the parameter is symmetric matrices, positive definite symmetric matrices size 2 is given as follows. Okay. We don't give a proof of this theorem, but roughly speaking, our paper suggests method to construct q-exponential family from trivial mu vt in a natural way and applies it to the triple that appeared in Poincaré distributions. And finally, we calculate the normalizing constant by using Wallis integral. If you are interested in, please see our paper. Thank you very much.
Thank you very much. So, do we have questions?
Hi, thanks for the nice talk. I just have a little question here. So, I'm not quite sure, but do you think the T distribution may be a kind of like under a framework?
Sorry?
Like it's a Q exponential and also like invariant under the SL2R? Is that, I'm not quite sure.
Student T distribution, right?
Yeah, the student T distribution and with location and the scale parameter. Yeah.
Student T distribution is not a Q exponential family because if T is T changes, then this corresponds to the Q, the fact that Q changes.
Okay, thank you. I need to consider it.
Okay, another question there.
Thank you for your talk. Short question regarding the Schwartz distribution space. Do you have a different description of the family, or do you thinking of to write one down? Do you think this is possible?
Sorry, one more please.
The space of generalized functions or Schwartz distribution space.
Schwartz distribution space.
So where you have also the Dirac distribution inside and all your families. So do you think of description interpretation of your family? Can you define that there? So for the case that the manifold is now an open subset of the RD. So.
I have never yeah, I have never considered that kind of that kind of things. So
maybe you can discuss maybe tonight as a gala. So let's thank the speaker again. Thank you.
Thank you very much.
Okay, so let me introduce you to our next speaker. So Professor Tanaka from Waseda University, and the talk is entitled Geometry of Parametric Binary Choice Models. Yes.
I have 20 minutes.
Yeah.
20, okay.
Can you use laser here and for one background?
Oh, I see. Oh, wow. Okay, let's start. Hi, nice to see you guys. I'm Hisa Tanaka, also Japanese. My hobby is to drink alcohol, but let's skip that out. my department is School of Political Science and Economics, so I'm social scientist. So I'm afraid I'm relatively somewhat stranger here in this hard science conference, but let me talk about some economics here. Okay, introduction, let me briefly explain my motivation with study. I'd like to talk about this binary choice model. Binary choice model, and let me briefly explain what the model is, because I'm afraid this model is called in different name in the field study. Y is output binary output takes 0 and 1 according to this condition, hold or not. Okay? X is observable random vector. Theta is canonical coefficient. Epsilon is a random term according to known F distribution. And Y denotes a decision made by an agent. Say a student comes to school or not, or goes to labor market or not, get married or not, and so on. X is observable variables like each agent's academic performance, income, and so on. Epsilon is an observable variable, some mental cost, and so on. So a person goes to college if the net benefit, this single index part, is greater than cost, then he will come to school, and otherwise he will not. And this type of model is very popular in labor economics, and I teach this model really often in the undergraduate statistics class and so on. And my aim today is to view this very popular model from the viewpoint of information geometry. Unfortunately, now let me continue the explanation of the model. The choice probability is computed as defined as the probability that this student gets active conditioned on his personality. It means the net benefit is greater than cost epsilon conditioned on x. It is given as f of x dot theta, right? Then joint density of y and x is given in this form. It just basically Bernoulli. And when the known distribution f is normal, then we say the model is probit. And if this f is a logic distribution, we say this is a logic regression. Okay? And the goal of my talk today is to view this popular model from a viewpoint of information geometry. And unfortunately, information geometry is not that popular in social science, in economics. And only a few papers are published in the Journal of Economics. For example, this is a book a famous book written by Marriott and Solomon in year 2000. And they studied the geometry of linear regression, Poisson regression, the ARMA model, and so on. The same authors and Kemp studied the world test geometry of world test of linear and nonlinear parameter constraints. And these papers are published in very good Journal of Economics. But not that many successors appear so far. So I want to add another educational example of application of information geometry to economics. It is a binary response model I showed in the previous slide. I will prove that this binary response model with or without linear parameter constraint is dually flat. Okay? And it is, I think, a good educational example how the information geometry works in economics. And also, the binary response models are dually flat with canonical affine coordinate, even though they are not linear, they are highly nonlinear, and they are not exponential, but still they can become dually flat. That's the goal of my talk. Okay? Then, let me introduce geometry on this model set. First, a manifold is defined as a set of binary response model indexed by, parameterized by canonical parameter theta. And the model's parameter set theta is supposed to be some open set in the d-dimensional Euclidean space. Y takes value either 0 or 1, X is a d-dimensional random vector. X is distributed according to some probability measure nu, and this is a joint probability. Canonical coordinate as shown before, theta. Then tangent space is defined as a span of a partial differentiable partial derivative operators. Okay? Then square function is just a partial derivative of log of this joint density. It is calculated as this. Okay? Now the model is formulated. Now everything goes straightforward according to the textbook of information geometry. Then the square function is obtained. Now the Fisher information metric is computed as a covariance of two Fisher two square functions as this. Okay? And this linear index structure of Fisher information metrics plays very important role to introduce the dually flat connection to this model. Okay? And this R is a function is given by this. Small f is the first derivative of cap f. So this f is a density function. Cap f is a cumulative distribution function. Once Fisher information metric is obtained, then Levi-Civita connection is computed according to this formula, well-known formula. And since the Fisher information metric has this linear index structure, the Levi-Civita connection also has this linear index structure. It means that parameter theta appears only in this linear index form. Okay? And what is more important here is that this Levi-Civita connection becomes symmetric among between I, J, and K. Okay, so everything becomes now obvious. Okay, obviously this space is flat because dually flat connection. Running out of battery, I think. No. Okay, dual connection is defined. Is obtained by subtracting the symmetric third-order tensor, Amari tensor, from Levi-Civita connection, right? And in this case, due to the linear index structure of the model, this Levi-Civita connection itself becomes symmetric. So we can employ this Levi-Civita connection as this Amari-Shentov tensor here, okay? So that the following result is obvious, I think. Okay, by theorem 1, dually flatness of the binary choice model. Binary choice model becomes always dually flat by choosing Levi-Civita connection itself as a symmetric tensor, the model set, and the Fisher geometry becomes a dually flat space. And theta is a canonical coordinate of the binary response model, becomes also affine coordinate, theta itself. No variable change is required. And also the dual affine coordinate eta is also given explicitly given by this equation 1. The first part of this theorem is obvious, so let me explain how to get this dual affine coordinate. Okay? It is easily done because, as I show, this the Fisher information metric have this linear index form. So it's easy to find out the potential function by taking the integral twice. Okay, by computing the partial derivative twice, we can go back to the Fisher information metric. By taking the first derivative of this potential function, we can find out the dual coordinate, the affine coordinate. That's it. Simple. Now the potential function was found in the middle of this proof by computing Legendre transformation. We can find the dual potential function phi here. Okay? And if we have dual potentials, two potentials function, then it's easy to compute the canonical divergence between two binary response models. P and Q are both binary response models, and the distance between the two models is measured by this second equation. And explicitly writing down this second equation is equivalent to this third equation. This is a canonical divergence equipped with the binary response models. So far, so good. Okay. So these all computations are very, textbook and good for the final exam of information geometry for undergrad students. But so far, no statistical point of view is introduced here. So let's move to the third section. Because the model is a statistical model, right? So the natural choice of divergence function is a Kullback-Leibler divergence defined as follows, right? And in our case, Kullback-Leibler divergence is equal to this sum of two expectations. The canonical divergence and Kullback-Leibler divergence are totally different, okay? If this D is a canonical divergence obtained from two potential functions, and the Kullback divergence are given here. In general, these two divergences are not coincident, but in theorem 3, these two becomes equivalent if and only if the distribution function f is logistic distribution. Logistic distribution is given by this fifth function. Okay, this is a if and only if condition. The proof is easy, just by taking derivative of the first one and the second one and set they are equal and solve some ordinary differential equations. Especially in case of beta is equal 1, means this beta is 1, then the f is called a standard logit distribution. Then here the Fisher information metric is here, f is density, and eta, the dual affine coordinate is here. And our potential function has this very well-known form. And of course, the divergence between P and Q is given here, which is equal to the Kullback-Leibler divergence. Everything becomes very simple. And the reason why logit model is so special is that it is, in some sense, belongs to the exponential family. Exponential family is formalized as the seventh equation, as well known. And the logit model and the probit model as a binary response model are not, does not belong to exponential family. But only the logit model, by taking conditioning on x, can be regarded as a kind of exponential family. This C1 disappears. The theta I becomes this linear index x theta. Beta iy becomes Dirac function. And a potential function is a conditioned potential function. Okay? And this is sufficient to get, to make the canonical divergence equivalent to the Kullback-Leibler divergence. To have that property, we don't need to have purely exponential family. Okay? Yeah, this doesn't work. And so we can generalize the result of the logit model into this theorem 4, the conditional exponential family. If the joint density of Z of W conditioned on W is written in this form, and then the conditional potential function is given by 10th equation, and the manifold of 9th equation becomes the Kullback-Leibler divergence of this statistical model becomes equivalent to the canonical divergence D of Q with potential function given by this. Okay. So we can generalize our result by the help of this theorem to the multinomial choice model. This multinomial choice model where this action Y is not binary anymore. Each agent can choose among some finite number of alternatives with this given probability. Okay. Then the model also becomes, because the model is still linear index structure, okay, so the model becomes dually flat, and canonical divergence, becomes equal to the Kullback-Leibler divergence. And this here is the dual affine coordinate to, it is dual to the canonical coordinate theta. Okay. Now, the one application by viewing logit model in this way is linear constraint regression. Okay. Suppose that this distribution function is a standard logit, okay, and consider a linear constraint hypothesis A node where this theta is trapped in this linear subspace. And in empirical research of labor econometrics, we do this estimation really a lot. Then, since this theta becomes affine coordinate, and since this space of a null hypothesis becomes an affine space of theta, this submodel where the coordinate belongs to this submodel becomes affine flat submanifold always. Okay? And we can think of projection with respect to Kullback-Leibler divergence by equation number 13, where for each given P is our original distribution, we can find another distribution Q, which belongs to the affine flat submanifold, which minimizes its Kullback-Leibler divergences. This solution of minimization problem is explicitly and nicely formalized, uniquely determined by this condition. If eta is a dual affine coordinate to theta, and if eta q minus eta p is orthogonal to this space H, then we can consider that this distribution is an orthogonal projection of original model to the submanifold spanned by the null hypothesis. Now here's a picture. This eta hat is corresponding to the unconstrained maximum likelihood estimation. And this eta tilde is a eta coordinate corresponding to the constraint maximum likelihood estimation. And this flat space H is a space subspace spanned by the null hypothesis. Okay? And it is natural to believe that the projection is a geodesic connecting eta hat, and eta tilde is orthogonal to this null hypothesis space. But it becomes orthogonal if and only if the binary response model is logit. If the model is probit, this doesn't happen. They are not orthogonally intersecting. It is very interesting. And in the logit model, these geodesics intersect with plane orthogonal, and the distance between eta hat and eta tilde is measured by Kullback-Leibler divergence. It is corresponding to the likelihood ratio test statistic. Okay? So by viewing the model from like this, we can give the geometric interpretation of likelihood ratio test, I think. Okay, so that's it. So I think this is a good educational example to teach what is information geometry to undergrad students of economics. Thank you. Yeah.
Thank you very much.
Yeah. These are references.
Do you have questions? Okay. Do we have questions? Okay, so maybe I can ask a very short question. Did you try to look at the convex conjugate as an egg-entropy to get the entropy of your binary choice model?
Mm-hmm.
Did you look at the entropy as the convex negative of the convex conjugate?
Oh, yes.
Can it be written nicely or?
I'm not sure. I didn't think about that. Well, let me think about it.
Okay.
Thank you. Yeah.
Okay. So let's thank the speaker again.
Okay. Thank you.